I'm really excited to announce our next speaker. So we have got Andrew Martin presenting next, and he will be speaking about who's afraid of the big bad supply chain. So Andy, I will hand over to you.
Thank you very much indeed. Right. Hello, good afternoon, everybody, and welcome to Who's Afraid of the Big Bad Supply Chain? I challenge you not to sing it in your head. I am from Control Plane, and thanks to the team that have helped and supported with this talk. Various bits of flagrant self-promotion while I'm here. SANS Sec 584, attacking and defending containers and Kubernetes is our leading course for SANS. Lots of red and blue team exercises in there, some author and coursework for O'Reilly, lots of training. I'd be remiss not to mention my excellent co-author, Mr. Michael Hassenblas, who has assisted and co-authored this Hacking Kubernetes book with me as well. Amazon informed me it is now available on pre-order. If you would like to help artificially inflate the bestseller list, this is a view on threat-driven attack and defense for Kubernetes, beginning with the humble pod, expanding through the other entities, looking at hard multi-tenancy and networking and admission control and policy, and finishing with organizations, detailing historical CVEs, and looking at how to threat model and defend your Kubernetes. But today we are going to talk supply chain, the great, expansive, and ominous supply chain that I'm sure you've heard lots about. It will be a hot topic at this year's KubeCon. It has been a hot topic in this year's presidential edicts and US organizations. So what is a supply chain? We'll start with an explain it like I'm 5. Then we'll look at how to attack it like we are a pirate. We'll look at signing approaches, which are one of the mechanisms we can use to defend ourselves. I know that Mr. Gareth Rushgrove also spoke about SBOMs, which is software bills of materials, which is another thing we can do. All integrates with signing. There are lots of technologies in this space, so I'll attempt to give a brief teardown, and then finishing with the grandiose Software Factory, a pipeline for creating pipelines, again comprised of a number of moving parts, and hopefully this will give you sufficient oversight to enter the fray. Copious oceans and wells of thanks to the friends and peers and colleagues who have done all the excellent work in this space to get us to where we are today. We're very much not finished, but there is a huge and exciting community of enthused individuals, and we'll talk more about these people and their technologies today. So what is a supply chain? First of all, it is so hot right now. Anything we depend upon can be expressed as a supply chain. In a military context, this is aircraft carriers being made from nuts and bolts and bits of metal. All of those things come from somewhere and are planned. From a pharmaceutical perspective, we've seen the supply chains that have affected the COVID vaccines. They are multifarious and distributed, and they need combining and coalescing and all of these things. At each stage, we cannot allow contaminants into the process. We must be sure that we have the right concentrations and all these kind of things. The same thing applies to food. We've seen a different part of the supply chain impacted recently in the UK, where an inability to ship food items, and I say ship, specifically that's lorries in the UK at the moment. So although the supply chain is able to generate or sort of breed and farm the food, we can't actually get it from farm to table. So just one portion of the supply chain being compromised or in some way damaged has a knock-on effect, and as a downstream consumer, we can no longer eat chicken wings, perhaps. Manufacturing, as popularized by Ford and Toyota, just in time, we can just bring in the things that we need from the supply chain onto the factory floor. And then finally, the superset almost of all of those examples, software. Software is comprised of other pieces of software that come from other places, built on hardware, running other software, running microcode. Yes, it's turtles all the way down. We will attempt to disambiguate some of those things. What's the point here? Well, as a consumer, we take and we trust whatever we're given as a producer. This is difficult because should we be trusting anything and everything? Absolutely not. We have seen this go badly wrong many times. So a software supply chain then, any code that ends up running in production. This is a malleable definition. I'm going to stick with production because production is where the lifeblood of the company, the customer data, flows and is stored and manipulated and used. So it's probably the juiciest place. It's where an attacker would want to get to. And what could possibly go wrong? Well, we can't be sure that our supply chain is competent at all stages, and it may be subject to events such as these, which, as I'm sure you can imagine, would take a few days to clear up. So, software supply chains. Everything is software. We've transcended various different Renaissance periods, and with cloud native, we can now define everything as software, as YAML, as code. Ultimately, we can package all of these things up into OCI images, and we have a relatively universal transport container, if you like, because an OCI image is just, of course, a collection of tarbles. So our software applications, yeah, of course, the infrastructure that they run on, the infrastructure is code, security and policy is code. We can put all of those things into a container and put them through specific pipelines. All sorts of different pipelines. We don't really mind that there's so much of this, but the point is, from a software factory perspective, these are all behaviors that we would defer to automation for. Well, what does that mean? It means that a build server, CI/CD, build automation, these things are remote code execution as a service. They operate on behalf of developers in order to complete tasks that developers would otherwise have to do themselves, such as cloning source code, building the thing, pushing container images, deploying to production, ideally with a GitOps workflow rather than a direct push. We've also got our security testing. We are scanning our dependencies, we're scanning our container images, we're scanning our networks, we're checking for expired TLS certificates, we're making sure that our infrastructure's code configurations don't change. If somebody goes through and does manual change, we're alerted, we auto remediate. And of course, we can do wider non-functional tests like our performance and load. The point is, these are all build server responsibilities. So the supply chain, everything is software. And we compose our software of other people's software, as I say, down to the microcode, which is a little terrifying. So we rely on the people who give us that code that we're depending upon for correct, non-violent, maybe kind and technically correct code. And as we see with the Alice, Bob, and Charlie example, anybody who is able to get in the middle of a supply chain can add an implant or malware or malicious code. And if that code sits quietly on its way to production and then suddenly is executed in a production context where it has access to customer data, or it can add itself to a command and control malware botnet type network, well, then we're looking at the beginning of a potential compromise that if it expands beyond the constraints of the initial impact point of entry, can be very expensive to clean up, might end up with a crypto locking infestation, that sort of thing. The point here is that any entry into a system is bad news for us. And because we're trusting such wide, long, expansive supply chains, they are difficult to secure. Arguably, full supply chain security can't ever really be reached. And we just need to raise our risk tolerance to a point that we're comfortable we're unlikely to become victims. There's multiple different types of supply chain attacks, and the compiler-based supply chain attack has been the new software security frontier for a number of years. With this gentleman, actually, Reflections on Trusting Trust. I'll talk a little bit more about that. But just looking at this question of trust again, we trust everything in a supply chain. The source code and dependencies that either we build or our developers build, or the GitHub autopilot accidentally backdoors for us, we must trust those. Our build systems, we're taking those component parts and placing them together into something that probably can't be introspected into particularly easily. This is where software bill of materials and a shopping list for the contents of built artifacts is useful, because you distribute a closed source artifact or a compiled artifact or an open source artifact equally, along with this bill of materials. And that allows us to know every single place in an organization that a potentially compromised package version is installed. But if we don't trust our build system and somebody ships us a fake SBOM, or they change a version, or they put, again, malware within the final deliverable, which is maybe a compiled artifact or a container image, well, then everything else is compromised downstream. The network that transports that thing to the application repository's contents at rest, finally deployed systems, any of these points are an avenue for compromise. And the nature of reflections on trusting trust is such that a compromised compiler can spit out compromised and backdoored binaries. This is, as I say, a philosophical musing that was backed up with code, getting on for 35 plus years ago, 37 plus years ago. Okay, let's look at how to attack a supply chain. Well, first of all, this is the 8-bit monstrosity Dread Pirate Captain Hashjack. He is hacking Kubernetes archetypal adversary and is typecast as a state-sponsored organized criminal. What does he want to do to your supply chain, I hear you ask? He wants to trick it into running his code in production. This is the goal: an implant, a backdoor, a botnet, command and control of some description in production gives us a jumping off point with which to attack the rest of an organization. What have we seen recently? We've seen REvil attack the Colonial Pipeline and shut down oil pipelines in the on the east coast of the US. That was done through a compromised supplier to the Colonial Pipeline systems. We have seen SolarWinds, which were attacked by a foreign intelligence service. Their build infrastructure was compromised, so that when a compilation of the SolarWinds product occurred, a malicious piece of code was added just before compilation time, and then the source code was removed directly after compilation time, so that there were no build artifacts residual in the build environment that led to, or that gave anybody reason to suspect something was afoot. What happened there? Well, SolarWinds was a highly privileged piece of software. It still is. And therefore, everybody who consumed that piece of software, SolarWinds being the supplier and Microsoft and the government in the US being consumers, they suddenly had a backdoor in their systems. And as we say, again, once you have that initial access to an organization's system, we saw multiple secondary and tertiary attacks occurring, especially against the government and US government and Microsoft, as a result of that initial supply chain compromise. CodeCov was a supply chain compromise within CI/CD infrastructure, and Xcode Ghost, even though it's a number of years old now, was a compromise of Xcode. So somebody was distributing a malicious version of Xcode that compiled a backdoor into all iOS apps it generated. There is a wonderful catalog of supply chain compromise, courtesy of the CNCF Technical Advisory Group on Security. If you would like to learn more about any of these things, they're a very friendly and open group, full of excellent contributions and white papers, and it's really a wonderful place to learn. This courtesy of that group then. How do we attack a supply chain? Well, we can go for the source code. This means getting access to a developer's end user device, an EUD, or it means stealing their credentials so that we can write into a source code repository. It might mean installing a keylogger so that we can get access to those things. It might mean getting remote access, yes, etc. The developer tooling, this is then the compiler type attack, or potentially attacking, as we can see, VS Code GitHub here on the right-hand side. The publishing infrastructure, once we have secured the source code and the tooling, if we're then building and distributing things from compromised hardware, well, once again, all bets are off. Trust and signing, maybe the build hardware is secure, but we've managed to steal the signing keys. So I can now build any piece of software, sign it with a legitimate key, and make it look as if your trusted producer gave it to you. Attack chaining is, of course, a superset of some of the above, and negligence is things such as committing one's keys to GitHub, and should hopefully be avoided by things like source code scanning. A note on source code itself: whether or not to sign commits with GPG keys is a matter of some contention. In my mind, it is better because this means that we provide a secondary or another factor of authentication to say very specifically, at this point in time, the person in control of this key liked this sufficiently to generate a signature. It's really all that it says. It's a human-based trust system, because ultimately this trust is all based on how humans interact. People have different views. The Linux source tree prefers to only merge or sign a merge commit, because that then implicitly trusts everything that was merged in one go. In my mind, for open source, the rapidity of change and the size of a pull request versus a kernel patch set means that just adding that extra factor gives us, in my mind, a lot more security. Sorry, a little bit more trust. There we go, very specifically. Of course, the source repository, this is preventing people getting access to hosted version control systems. If we're hosting our own, it is imperative that access to those is constrained and that the operations team managing them are restricted as well. Same for the build infrastructure. It's normally a soft underbelly of any organization's collective software delivery pipelines or lifecycle, I suppose, because, again, we're ceding control to the machines, rightly so, but that requires some level of access for debugging complex and advanced Heisenbugs and non-determinism. We can infect a trusted supplier. This is very much the SolarWinds style of attack. And yep, we can also go upstream to attack things like NPM or Maven or Ruby gems. And then finally, we can say, well, let's ignore the whole supply chain, except for the runtime environment. If we ship a compromised container, then when all the good code comes and runs in that container, we can still get access to it because of a backdoored operating system component, and then we can steal the keys that have been added, or spoof the identity, masquerade, and legitimately access things and data stores that are around the place. So, Salsa is a supply chain security framework from Google. It broadly predicates itself on hardened infrastructure in the first place, which may or may not be the case. But if we look at all the places that we can attack a very simple pipeline: code review from the developer, the source control system itself, the code as it's in transit from the source control system to the build server, the build platform, so the build steps that are building the thing, or a Jenkins or a Tekton, a bad dependency. So this is an upstream attack against NPM, for example, and we'll demonstrate one of those in a moment. Bypassing CI/CD entirely, so having direct access to the packaging repository and just tampering, adding some malicious code, and publishing a new version. We have a compromised package repository itself, so maybe an internal actor has manipulated that, maybe credentials have been stolen, maybe someone has got access through a vulnerability. And finally, just using a bad package in the first place, as in the package was there, but yeah, we've then pulled it and become compromised in some way. Here is an example of, I've got a few examples, a few demos, but in the interest of time, I'm only going to do the first one, and the longer version of this talk will include a couple more. What will we do here? We will firstly not do that. Try this. There we go. So we have got, okay, so this is an npm package JSON. So I'm going to try and install this as if it was from the public registry. It's not on the public registry because it will, excuse me, I will be flying soon. It's not on the public registry because it's malicious, and I wouldn't like to do such a thing. What is notable here is that there is a pre-install step. Why is that a bad thing? Because when we go to install this package, before the package is even installed, it runs my shell script. You may be able to infer from the name exfil what it does. It's backdooring applications, installing a keylogger. It's just enumerated the contents of my GPG and SSH keys. This is a good reason to run second factor authentication because it's very easy to steal these things, and there's not very much that we can do about it. We need to make sure that what we pull from these third-party systems is trusted. The best way of doing that, unfortunately, is to denormalize them into a local proxy or cache of some description and make sure that they're of a decent quality before they're pulled. This involves a lot of manual code review. It is not a great look. So we should be cognizant about exactly what we're using in these contexts. And yeah, air gap is probably not practical for everybody. What else can we do? We can backdoor a container. So if we are running Kubernetes and I trick you into running a container image or building a container from a compromised base image, when it runs in production, it makes this reverse TCP connection to a port that I'm controlling and listening on somewhere on the public internet. It's an outbound connection, so it's going backwards through the firewall in the opposite direction to how an internet-facing firewall is traditionally considered to operate. And that gives me access to your Kubernetes. There's numerous ways to not get around, but to protect ourselves here. Of course, we know about scanning images, minimum viable cloud native security, intrusion detection. We shouldn't be opening shells. We shouldn't be spawning shells or opening network connections to the internet. We can do better than nothing there. We can do build time behavioral analysis to pick this kind of stuff up. So does the implant fire when it's put into a malware lab type environment? We can use eBPF tracing to detect some of the intricate details of what are being done there. This is this is on the bleeding edge. It's not so widely it's not really widely deployed at the moment, but we've been doing some interesting proof of concepts around that work. And of course, this is all just predicated on we must have a good security context and capability config. Shout out to kubesec and the OCI seccomp BPF hook for deriving seccomp profiles using eBPF. Okay, what other forms of build compromise might we have, or supply chain compromise here? Let's just think about exactly how we build software for a moment. So, courtesy of Dan Lorenc, who has numerous images in the next few sections and pieces of software as well. We start with the software configuration management repository. The build system grabs our source code. It builds an artifact, which is probably a container image for us. It may be a compilation of a binary, and it generates provenance. That is a way of saying, I have done a thing, and here is a cryptographic signature to prove that I did it. When we go to deploy into production, we use a policy engine to prevent things that do not have provenance records being deployed. And we will come back to this concept. This is now the target of how the software factory and the secure build system is intended to work. Get thee to KubeCon if you possibly can. This is why I'm traveling now, in order to try and get in time. Mike Lieberman and Timothy Miller will be demoing some really interesting attacks on compilers. And this is some of the work that we've been doing over the past year or so. And there's an end-to-end example in here where signed images are tested at admission control time, in this case by Kyverno, to make sure that everything that is deployed to production is signed. So these are container images right now. We have been a number of years getting up to this point, and I'm very excited to say that we are close to it. Another song inspired interlude here, Sign Me to the Moon. All right, in the last few minutes then, what is signing? Signing is the combination of two entities, a key pair and a piece of data, to create a signature and use that signature later to reverse the process and verify that the data matches the signature using the public portion of the key pair. Distributing the signature alongside the data gives us verifiable certainty that the contents of the signature or the metadata in it was signed by a person who trusted it at that point in time. And we're really back to this, this concept of human trust. In-toto is a tool to support this in the build pipeline. So for Tekton chains, which is a Kubernetes-based build system, and chains is the attestation part, the signing part. In-toto is the core technology. So between the checkout of code and the build and the test, each of those events is tested against a layout file like this. So we're looking at a step to say, create this. When we do a git clone, we expect this demo project foo py to exist. If that does, a piece of link metadata, as we can see, those signatures is generated. And that forms a chain of trust that we can use to tie together all of the build stages. So far, so good. That's only the build stages. We're going to create a signed artifact at the end. We want a container image. We want the container image to have been built securely, but also be provably secure. This is where we get into container signing. This has been a slow-moving space for a while. Notary was the original and best, but we have now seen cosign and recore turn up from the sigstore project, which provide a much simpler way of doing what Notary was doing before. Recore specifically is interesting because it provides a transparency log analogous to a certificate transparency log for metadata and signatures of arbitrary things, in this case, container images. This gives us trust that everything that's been signed is publicly visible and verifiable, and that the keys that we use are verifiable externally. It should be noted with bells on that this is all about trusting people. Software does not compromise itself. A lack of transparency into software composition is suspicious, and don't let people tell you otherwise. Open source software is by definition open, and chicanery and prevention of transparency, obfuscation perhaps is the word, shouldn't be accepted. We really must do better as an industry. So what we're looking at here is not only the signing and publishing of the artifacts, but the certificates that go with them, and those public logs so that we can monitor them for signs of compromise or a lack of a signature that we expect. Before we get finally into the software factory, one more concept is Spiffy. This is a way to try and replace passwords by giving everything an identity. It is a root of trust based system, and it is the core technology in Istio that enables workload identity and mutual authentication between microservices. Spiffy and in-toto glue together with this bit of code. Again, another fantastic team that we've been collaborating with this year to try and get some of this stuff over the line. And they forked in-toto and added the SPIRE workload API so we can verify in-toto certificates based upon X509 certificate constraints. With all these underlying pieces of technology, we get to a software factory. A software factory builds other software factories. It is a pipeline for building pipelines. This means it is DevOps on steroids. It really requires very well lubricated pipelines, etc., and it's aggressive automation. We care about the whole shebang here, from infrastructure to application. Any one of these points in a software factory may be compromised and then would invalidate the level of trust that we place into these things. The Department of Defense has a reference design for these things. It is up and running with the Castle Run program. Everything is automated is the core line here. And the CNCFs, Tag Security, once more are doing exceptional work and building out a reference software factory architecture. So what we see here in the middle is our CI/CD pipeline. We're orchestrating these, the fetching, the building of the artifact, and the publication. And then at the bottom of the diagram, not the SDLC services, but the last green layer, we see an identity attester. And that is taking metadata about the behavior of about the metadata about the properties of the tasks and using those to generate an identity, which can be used to integrate with the rest of the system. And this fundamentally is the idea that we give everything an ephemeral identity and we don't use username and passwords across the way. It fits with all the good stuff we've been talking about in-toto, sigstore, cosign, recore, Spiffy, SPIRE. There is a lot of complexity here, and things are really just emerging and getting underway. I urge you, if of interest, to jump in. And Dan Lorenc, who is one of the authors and founders of the sigstore project, has a zero trust supply chain paper, which I recommend very highly. I hope that's been an interesting introduction. Thank you very much for your attention. And yes, beware of the supply chain. Thank you very much.
That was great. Thanks, Andy. We did have one question that got posted into our Slack channel. We've probably got time just to answer this one, so that's worked out well. So the question is, if there are no current checks in the current pipeline, where do you suggest people to start with in their supply chain security journey? Assuming breach is a good approach to take here.
That is a very good question. We can defer to the salsa document for an answer. Salsa level 1 recommends collecting provenance information, and even if there are no checks and we don't trust the supply chain and the build infrastructure itself, just collecting what is essentially metadata and SBOMs about the things that we're building, even if it doesn't protect us, gives us some view of historical provenance, and in the event of a compromise, we can start to build up some idea of how it happened from there. After that, of course, we do want to have slightly more trust and start to include some of these signing systems so that we can cryptographically prove that what we said at the time and signed hasn't been tampered with and was true.
Okay, interesting. Thank you. I don't think I've heard a talk where someone mentioned the word chicanery either, so I particularly enjoyed that. Thank you. Okay, so if anyone else had more questions for Andy, then please post them into the Slack channel or into the YouTube chat.